In the last lecture, we studied single variable optimization methods which use derivatives. In this lecture, we will study the other class of methods which do not use derivatives. These are called region elimination methods because iteration by iteration, these methods strive to eliminate part of the domain, part of the region itself. So suppose we have evaluated a function at 3 points and have a bracket. At A, the function value is high. At B, the function value is high. And in between, at x bar, the function value is low. So we have a bracket. Now, all that we know is that the value at x bar is less compared to the values at A and B on both sides. That doesn't mean that this value is the minimum. The minimum may be somewhere. Between A and B, there is a minimum, this much we know. But where, we don't know. It may be at x bar, it may be before that, or it may be after that. So this is FA, this is Fx bar, and this is FB. So between A and B, there is a minimum point. We know that because we have the mid dip between the two extreme points. But whether the minimum is on this side, as the green curve shows, or on this side, as the red curve shows, we don't know. Fine. But we can evaluate the function at some arbitrary point, say x bar at this point, at A, x prime. So at A, x bar and B, we know the values. At x bar, it is least among these three. But at x prime, a fourth point, we can evaluate the function. If the function value at x bar, this new point, turns out to be higher than this, somewhere here, then we will know that the actual profile of the function resembles something like the one that you see green here. Okay. In that case, if the function value here is higher compared to this, then we don't need the bracket from A to B. We can take the bracket from A to x prime. Okay. Because in between we have a lower value from both sides. Because this is already lower than this, and this just now we found to be higher, so this is lower. On the other hand, if at x prime the function value turns out to be lower compared to this, then we can remove this part of the original interval, and then we can concentrate on this side, because here high, low, high, like the red curve. So that means based on our new evaluation, whether it is lower than this middle value or higher, we can eliminate this segment of the old interval or this segment. In any case, the resulting interval, whether it is from A to x prime or x bar to B, will be lower than the original interval. So this is how the regional elimination methods operate. Iteration by iteration, through new evaluations, they try to go on squeezing the bracket. Okay. So that is why, since they eliminate part of the interval, eliminate some region from the interval in every iteration, that is why these are called region elimination methods. Simplest is interval halving. Say from bracketing, we inherit three function values. At the extreme points of the interval, A and B, and the midpoint, xm. This is what you would get if you do the bracketing by constant step size. Okay. So you evaluated here, 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 and discovered the bracket. So at the two extreme points and at the midpoint, you have the function value. Midpoint value is lower. Fine. So these three function values we inherit from the bracketing. And in the first iteration, we evaluate the function at x1. That is, the midpoint from A to XM. Okay, so the A to XM is half the current interval, and this is at its half. If here the function value turns out to be lower than this, then it has to be lower than this also, because this itself was lower than this. So if at x1 the function value is lower than at xm, that means that this value is lower than both of these. In that case, we can take this as the next interval. Okay, so this xm is then renamed as b, and this x1 is renamed as xm. That means whatever was the scenario earlier with a xm b, now will be the scenario with a x1 xm. So that is why x1 and xm are renamed as xm and b. And then with the half size interval, we can go to the next iteration. There again, we will have the two extreme values and the mid value, and we can continue. If the function value here is not lower than this, say higher, then fine. Like this first quarter, then we evaluated the third quarter at x2, evaluated x2. If fx2 is lower than this, then rather than this side, it will be this side. So that is this 2 is 2. So then xm is renamed as a. Now the new a is here. x2 will be renamed as xm. The new midpoint will be here. And we proceed with this interval for the next iteration. If this is also higher compared to this function value, then you see, here also the function value is higher than xm. Here also the function value is higher than xm. In between, at xm, the function value is lower. Then the middle half, leaving out this quarter and this quarter, the middle half will give you a high, low, high pattern. That is the case 3. Okay, that is this. In any of the three cases, you come out with half size interval compared to earlier. So this is what is called the method of interval halving. In every iteration, you halve the interval, either this initial half or the last half or the middle half. Fine. So bracket size reduces by a factor of 2, and you need to make 2 evaluations for it. One at the first quarter, one at the third quarter. Okay. So payoff to cost ratio, reduction factor is 2, number of evaluations 2. So 1. Fair enough. Now, as you continue with more iterations, you find that the size of the interval goes half, quarter, 1/8, 1/16, and so on, geometric progression. On the other hand, number of evaluations will be 2, 4, 6, 8, arithmetic progression. So with more number of evaluations, the advantage will be higher. Okay. So for comparing this method with other competing methods, you can take the product SE. Okay. That is final interval size into number of evaluations per interval, per iteration. So that will give you the number of the payoff to cost ratio over a number of iterations or a number of evaluations. Okay. So this is one method. Let us see an illustration of this. The same function for which with which we saw the illustration of quadratic estimation method. So here, and the same bracket, okay, 2 to 4. So in the beginning of the first iteration, we have the function values at 2, 3, 4. And then as part of the iteration, function is evaluated here and found to be higher than this. So it is evaluated here and then found to be lower than this. Okay? No? Yes. No, this is also higher. So now both are higher, so the resulting new interval will be first quarter to third quarter. So in the next iteration, this goes here, and this stays here. It's the middle half. So at the end of the iteration, the size of the interval becomes 1, evaluation 2. Okay. So here in the upper line, it is number of evaluation and therefore the product SE. Here, another value has been shown as EM, maximum number of evaluations. Why? Because for the case of interval halving method, the required number of evaluation maximum and actual number of evaluation in a particular iteration may be different. Because if x1 itself turns out to be lower, as happens in the third iteration, this turns out to be lower than this. In that case, this is not at all evaluated. So there is a saving here. So in this case, you see, number of evaluation will be 1 less, but maximum number of evaluation would be full 2 into 3, 6. Okay. So like this, you can go on, and sometimes the middle half will survive, sometimes the initial half, sometimes the final half will survive. And in 6 iterations, as expected, there will be at most 12 evaluations. As it happens, actually 10 evaluations are made, because in the third and in the 6th iterations, the first half survives. So one evaluation is less in these 2 iterations. So finally, after 6 iterations, what will be the reduction in the size of the interval? So half, 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 6 times. Okay. So it will be 1 by 64 of the original interval size. And that is this size, 0.3125. Okay. 0.3125. That is 1 by 64. And the number of function evaluations in between, maximum it would be 12, but we have been lucky in 2 iterations, so it has been actually 10. So depending upon whether you take the maximum number, which will operate in the worst case also, in that case, over 6 iterations, it is this payoff to cost ratio. On the other hand, if you consider the actual number of evaluations, then it is this. So keep in mind, make note, 5.3 to 6.4. That is the case over 10 to 12 iterations, 10 to 12 evaluations, 6 iterations. Now, for every iteration, 2 evaluations, factor of 2 deduction. Can we do better? Okay. That is, with 1 evaluation, can we reduce anything? So if we can do that, that will be an advantage. So such a method is what we see next. And that is called Fibonacci search method. It works on the basis of something called Fibonacci sequence. And that's a sequence which is very great favorite of mathematicians, because it has enormous number of interesting properties. Its definition is a sequence in which the 0th element is 0, first element is 1, and that point onwards, later F2 onwards, get defined by this recursive relation. F2 is F0 plus F1, so it will be 1. Then F3 will be F1 plus F2, F1 plus F2, that is 2. F4 will be F2 plus F3, 3, and so on. And this sequence goes on. Okay? So this is called the Fibonacci sequence. And it has a lot of interesting properties. This recursive definition, this sequence has a lot of interesting properties. And in particular, one of those properties gives us an interesting optimization method, which is economical. Let us see how. Pick up a number from this sequence, Fn. Okay. Say we take n as 11, so Fn, F11, that will be 89. So we have picked up a number from this sequence, F11, which is 89. Now, consider our bracket A to B with whatever we start, and consider it in split in 89 parts. Okay, as if 1 by 89 of the bracket size is our unit. Okay, so what is the size of the unit? Delta, that is bracket size S divided by Fn. S by 89 delta, that is the current unit in which we measure interval length. Now, identify two intermediate points in the bracket at A to B. First one by this convex combination of A and B, and the second one by this convex combination of A and B. Why I said convex combination? Because Fn minus 1 plus Fn minus 2 is Fn. That is from the Fibonacci sequence property. So the sum of the two coefficients is 1. Fn minus 1 by Fn and Fn minus 2 by Fn. That will be Fn by Fn. That is 1. And each one of them is a positive fraction. They sum up to 1. So that is a convex combination. So that is why the resulting point will be a point in the line segment joining A and B. Right? In between A and B, it's a value. This is one value, this is another value. Now these two are complementary convex combinations. You see, the coefficients have interchanged. So x1 will be 34 units right of the lower limit, and therefore 55 units left of the upper limit, higher limit. Okay, because 34 plus 55 is 89. That is the number of units that we have. Similarly, x2 is 55 units right of the lower limit, and therefore 34 units left of the upper limit. Okay. So, and these two, 55 and 34, happen to be the next two Fibonacci numbers downward. Okay. So this 89 is split in 55 and 34. Okay. Now, these are the 2 points inside the interval where we evaluate the function and compare between them, okay, in the iteration. So wherever we find the lower value, we eliminate 34 unit of the interval length from the 89 unit length, retaining 55 units. Okay, see this. This is A, this is B. So in that unit, if you write, then this is 34, this is 55, and this is 89. 89 units from A to B. At 34th mark, we have x1. At 55th mark, we have x2. Now, the way Fibonacci search method operates is that we evaluate the function here and here and compare these two, which is low, which is high. If this is low, then we want to keep this initial 55 unit of the interval. On the other hand, if this is low and this is high between these two, then we keep this 55 unit of the interval, okay, the later 55 unit. In any case, the lower value is retained as an interior point, and between these two, the higher value, whichever is the higher, that will become a boundary point. And if this becomes the boundary point as high, then this will go out of business, because from x2 to b will be chopped off. Similarly, if this is lower, then this remains as interior point, this remains as the boundary point, this becomes the boundary point, and in that case, this part of the interval gets chopped off. Okay. Now, suppose this turns out to be lower, and then this part remains. Now, this time it is 55 units long interval, and therefore, according to Fibonacci sequence business, that 55 unit interval will be now split into different parts by putting two interior marks, one at 21, the other is at 34. Okay. The point at 34 mark is already there. Okay. And then new one will come here, 21. So that means in the next iteration, the two interior points where evaluation would take place, out of that, at one point, the function value is already available. We do not need to evaluate it further. Only one more evaluation will be needed. If you keep on this side, that is also 55 units long. So here also 21 and 55, 21 and 34 will be the location of the 2 points. The first one is already there at 21. Okay. Next one has to be evaluated. So whichever side, whichever unit, left side or right side you keep, for the next iteration, there is a saving of one function evaluation, because that happens to be coincident with one of the points in the previous iteration. So this is the advantage of Fibonacci search method, that by putting the interior points at such interesting locations, you are ensuring that one of the 2 points every iteration turn out to be from the previous round function evaluation. So every time you evaluate a function, you actually end up using it twice. Now once, next iteration once, and perhaps later also. So every iteration, you will evaluate only one new point. And what will be the size reduction in the interval size? There is certainly some reduction. Say 55 by 89 first time. Next time it is 34 by 55. Basically, it is fk minus 1 by fk. And that is less than 1. Okay. So one function evaluation and some reduction. In the case of interval halving, we saw 2 by 2. Now here, 1 point something divided by 1. So that is an advantage. Okay. So this is how Fibonacci search method has a marginal advantage over interval halving. Now let us see a sample run of the same problem. Bracket 2 to 4, 2, 4, and then x1 and x2, fx1, fx2. Okay. Interval size is reducing like this. Evaluation, first iteration is 2 evaluation, can't help it. And that point onwards, every new iteration, only one new evaluation. Okay. And in 10 iterations, 11 evaluations take place, because except the first iteration, in every iteration, only one new evaluation. And you see, after 10 iterations, it is not possible anymore to conduct the 11th iteration, because it was started with F13. Now, this is a little peculiar thing with Fibonacci search method, that if you start with Fn, then only n minus 3 iterations you can make. So with F13 we started, and after 10 iterations, you see where we have reached. You can see this actually. See, F13 is the next one. So then the 2 parts, I mean F13, so next round it will be at the 2 marks will be at 89, 154, 144, that is 1. Then second round it will be here. Then third round it will be here. These 2 will be the locations. 4th, 5th, 6th, 7th, 8th, 9th, 10th. At the 10th round, you have 3 units left, and the first one is at 1 unit, second one is at 2 units. Whichever you take, you end up with 2 unit length left, okay, say from here to here. And then the 2 points will merge, because there is no space anymore, okay. So after n minus 3 iterations, the process automatically ends, because this last line is not actually not 11th iteration, because that iteration is meaningless. The new point that is coming here, 3.1416, was already there. Okay, so after this, the two interior points merge and there is nowhere to go. So there is a natural termination for Fibonacci search method. Okay, so in interval halving, we saw 6 iterations, which should have taken 12 evaluations, but luckily it took 10 evaluations. So 10 or 12, whatever you take. So Fibonacci search method, since we started from F13, in 10 iterations, we made 11 evaluations, and see the advantage is quite high. In that case, it was 6.4, okay, per function evaluation. Here it is 10.5. So it's much more efficient compared to interval halving. Now, starting with Fn for an interval and using XL to XU to denote changing intervals, how much uncertainty is there? You can work it out. Say XL is the lower limit, XU is the upper limit in a particular interval. X1 is the first mark, X2 is the second mark, interior mark. So basically these two interior marks split the entire interval into 3 parts. X1 to XL to X1 of this length, X1 to X2 of this length, and X2 to XU of this length. Now this length and this length are same. This one is lower, smaller, okay? So the maximum of this is this, and therefore this much is the uncertainty. So at any point, wherever you terminate, you get one of those points, X1 or X2, whichever one is the most recent one, and the maximum uncertainty that can be is this much on this side or this much on this side, right? So they are unequal. So one is the smaller one and the other one is either this or this. So this much is the uncertainty. So now if you can work out iteration by iteration, starting from Fn, the 2 marks will be at Fn minus 1, n minus 2, and therefore the locations of those will be x1 will be xl plus this much into the size of the original interval, and x2 will be xl plus this much into size of the original interval, and the final interval size will be in any case fn minus 1 by fn, either this side or this side, okay, either a to x2 or x1 to b, okay, both will be of the same size, and uncertainty will be either on one side n minus 2 by fn, fn minus 2 by fn, on the other side it will be fn minus 3 by fn. The larger is this. So this is the maximum uncertainty. This is the in the first iteration. After first iteration, the interval size will be S1, okay, which is this, okay, and therefore that S1, if you put this in the second column, then you see fn minus 1 by fn, multiply it here, then fn minus 2 by fn you will get. And like this, you can go on iteration by iteration, filling up the columns. And finally, after n minus 3 iterations, you get this as the size of the final interval, and this as the uncertainty. And finally, at the last iteration, the uncertainty on both sides turns out to be same. And that is why in the next round, that point will be repeated again, and therefore that iteration is meaningless. So this is the final uncertainty. And you have to start enough high so that by the time you come down to the F3, F2 level, okay, where it naturally terminates, F3, F2 are actually 2, 1. F1 is also 1. F0 is 0. So by the time you come down to that, you should reach the tolerance with which you wanted to report the solution. That means this needs to be pretty small. Okay. So to ensure delta x, that is uncertainty S0 by Fn, is less than or equal to a given tolerance, say you want the solution to be correct up to 3 places of decimal. 3 places of decimal. So for epsilon you want 0.001. Okay. So if that S0 initial bracket size you already know. So based on that, S0 by epsilon will give you the corresponding Fn. Okay. S0 by epsilon will give you Fn. And that should be this. Okay. So that means since there will be a natural termination, n-3 iterations, after that you cannot continue, it will become meaningless. The same thing will repeat. Okay. So to begin with, you have to decide how high we start. Okay. So from b minus a by epsilon, whatever is the number this gives, after that, the next higher Fibonacci number has to be picked. Accordingly, n will be decided, and therefore the number of iterations n-3 will come out. And that many iterations you can take, exactly that many, not more. Okay. So this is how Fibonacci search method works. And we have seen that it has a minor advantage of efficiency over interval halving method. Now, it is an improvement over interval halving in the sense of interval size reduction per function evaluation. However, there are two awkward things, funny things that operate in this method. First is that the interval size decreases at a variable rate. So the algorithm operates at a variable rate. And depending upon the tolerance that we need to decide to begin with, where do we start? But then at the end, where the end comes, we have to end it. After n-3 iterations, even if we want to continue, we cannot continue in the same sequence. And this is a little awkward. Both of these unusual facets can get regularized in a slightly variant method. And for that, make note that if we start at a very, very high Fn, okay, then what happens? As k tends to infinity, the ratio of consecutive Fibonacci numbers, fk plus 1 by fk, this ratio converges to a finite ratio. Call it phi. And if it converges to a finite ratio, then with k very large, this ratio between k plus 1 and k plus 2 and k plus 1 will be almost same. So equate that. Then according to Fibonacci number property, fk plus 1 can be written as fk plus 1 plus fk. And now you see this is fk plus 1 by fk plus 1, that is 1. And this is fk by fk plus 1. Reciprocal of this, that is 1 by phi. So if you equate phi to 1 plus 1 by phi, then multiply with phi, you get phi square equal to phi plus 1, or this. Now that means the constant ratio to which this tends, that number phi, that ratio phi will satisfy this quadratic equation. And you can solve it. Of course, in the solution, one solution will be negative, the other positive. The positive solution of this one, this is an irrational number. And interestingly, though irrational, it is called the golden section ratio. Okay. And this is a very famous number, golden section ratio. And it has a lot of significance in diverse fields, in science, engineering, even biological science for that matter. Okay. And apart from that, it has got on itself imposed upon it a lot of aesthetic overtones. For example, you will say that a shape looks nice if the length to breadth ratio is close to this ratio. A woman looks beautiful if her face has a shape of length by width, which is something like this. For that matter, this slide shape does not look bad to you. It looks reasonably fine, perhaps because the width to height ratio is close to this. Okay. So this kind of aesthetic overtones are imposed on this particular ratio called golden section ratio. Now, if we say that we will go by Fibonacci search method, but start very high, as if we are going to take infinite steps. Okay. So for the time being, let us pose as if we are going to make infinite iterations of Fibonacci search, starting with a very large n and therefore very large fn. Whatever large they may be, we still get the advantage of one of the evaluation points in every iteration being coincident with one of the previous evaluation points. Fine. And more interestingly, even if we do not know how high we are starting, if the interval size is known, S, A to B, okay, then where the two interior points x1 and x2 will be, we know, because x2 will be 1 by S, 1 by phi size, because Fn minus 1 by Fn will be 1 by phi. So x2 will be XL lower limit plus 1 by phi of the current interval size. And 1 by phi is the same as phi minus 1 from that quadratic. And x1 will be another phi section down. So that is why lower limit plus s by phi square, which turns out to be 2 by phi from the same quadratic. Okay. So we do not need to know whether Fn is the 20th one or 40th one or 70th one or 100th one or 1000th one. We don't need to know. In any case, where the two marks would be, that we can get from the golden section ratio itself. Okay, because we know that Fn and Fn minus 1, Fn minus 2, all three of them are very large. So we put the interior marks x1 and x2 according to the ratio, golden section ratio, every iteration. Okay. So we start at infinity and end also at infinity. That is as if we are starting from 10,000 step and coming down to something like 980. Okay. So that both are very large. So every time the reduction is by a section ratio, which is golden section ratio. And before we come down to small size, we actually terminate. Okay. So the resulting method is called golden section search. And here in every iteration, the interval size reduces by the same constant factor. And that is golden section ratio. And we, of course, do not make really infinite iterations. That is meaningless. Now we need to work out how many iterations we need to make to achieve a required tolerance epsilon. So you can see that B minus A is the initial interval size. In every iteration, the interval size reduces by a factor phi, which is the golden ratio. And at the end, it will be B minus A by phi to the power m. But then the uncertainty will be another section. So m plus 1. And this uncertainty should be less than equal to the given tolerance, epsilon. Based on that, we get phi to the power m plus 1 as b minus a by epsilon. And therefore, from that, we can work out m by this logarithmic ratio. And whatever is the next integer, we take that m, and that many iterations we can conduct, and the tolerance will come down like that. So from the initial interval, the final interval will be accordingly small, and the tolerance will be within that. Okay. So this is the number of iterations required. So this is how golden section search operates. And the same example, if we try with golden section search for 10 iterations with 11 evaluations, we get this. It is a little better compared to Fibonacci search method, so far as this bracket shortening rate is concerned. Okay. If you compare all three of them together, then you will see the best X star found, the uncertainty that we have at the end, the best function value, the error in function value from the absolute minimum. Absolute minimum happens to be pi actually at X star equal to pi, and the function value is 1. Okay. So of that function, number of iterations, which means number of evaluations here, and this. Now you see the data here in these three columns, X star, delta X, and F star and delta F, these are incidental. And they will vary from case to case, example to example. Okay. And therefore, the Fibonacci search method just hitting bang onto the actual minimum value, that is of not great significance, because here it just happened that according to Fibonacci numbers, the value of X, one of the interior X's turned out to be that. That is not going to happen every time. Okay. So what is going to happen is this interval reduction at what rate? So over 10 to 12 iterations, interval having reduced the interval of size 2 to 0.03, Fibonacci search reduced it to 0.0172, golden section search reduced it to 0.0163. So golden section search turns out to reduce it to smallest value. Okay. And rate of the squeezing, if you see, you get this. Okay. Data about the number of function evaluations and progress rate corresponding to a given number of iterations is general. That will operate for whatever function you take, because we are reducing the interval size according to a planned rate. Now here there is a question that we will actually come across many times in different contexts. Without the knowledge of X star and F star, we would never know delta F. This column and this column that you see here, that is because I have supplied the two true X star and F star. But in an actual scenario where we are trying to find them, we do not know them a priori. So these two we will not know. At most, that what we can know is the maximum of delta X. Okay. So that we get from the interval size reduction, which you find here. Okay. The uncertainty cannot be more than that. In that sense, we get that information. And delta F, we don't given even there, because all the time we are approaching F from upper side because we are minimizing it. True minimum we don't know ever. Okay. So how lower it could go, we don't know. Okay. So all that we can figure out is the difference between the two successive function values. Okay. So in an actual algorithmic scenario, what should be our termination check? Typically, there are three possible checks. One is convergence in variable, that is two successive variable values, whether their difference has gone down below a particular threshold, or convergence in function values, that is the difference between two successive function values, whether that has gone down below its threshold, or the first order condition if the method uses derivatives. if the gradient magnitude has reduced below a particular threshold. And now these three thresholds have no reason to be the same because they are different quantities, their units are different, and so on. So these can be three different threshold values depending upon their individual scales. Now these are issues which we will come across in many algorithms, and some algorithms operate with this, as we have done in the region elimination methods. On the other hand, the derivative-based methods were operating based on this. Some algorithms operate based on this threshold, this check, and some algorithms operate with combination of some of these checks, two of them, okay, or three of them. Okay? So these are the three quantities on which we typically try to keep monitors for exiting an algorithm as a check for termination. So what are the important things that we did in this lecture? So we studied region elimination methods, which start with a bracket and iteratively shrink it by function evaluation only, without derivatives. We studied three region elimination methods: interval halving, Fibonacci search, and golden section search methods. And this is a question which we have come across in this lecture, towards the end of this lecture: convergence in the variable, constancy of the function value, and first order necessary condition. These three are competing notions for potential termination conditions in descent-based iterative algorithms, and we will come across them against many other algorithms as we proceed. So in the next lecture, we will study an important topic called line search, which is based on single variable optimization, but has application for multivariate optimization. Thank you.